Today, we are taking a journey to the edge of space-time itself. We're going to be talking about the most extreme, most mysterious, and frankly, the most powerful objects in the entire universe. I mean, these are places where matter is just crushed beyond all recognition, and where time itself behaves in ways that, well, they just defy all intuition. They are the ultimate cosmic enigmas. Okay, let's really dive into this. And look, this isn't just some hypothetical. It is the central question that defines a black hole. So today, we're going to break down exactly what that means.
So to really get a handle on this, let's start with something familiar, Earth. If you want to launch a rocket off our planet and never have it fall back down, you need to hit about 11.2 kilometers per second. That's what we call escape velocity. Now, a black hole is simply an object that is so incredibly dense, so compact, that its escape velocity is faster than the speed of light. And since we know nothing can travel faster than light, that means absolutely nothing can escape. Not a rocket, not a planet, not even light itself.
And this right here illustrates a super important point. Black holes aren't about being big, they're about being unbelievably dense. To put it in perspective, for our sun to become a black hole, you'd have to crush all of its mass down into a sphere just 3 kilometers wide. And what about Earth? You'd have to squeeze our entire planet down to the size of a tiny marble, just 9 millimeters across. So they aren't some kind of cosmic vacuum cleaner, not really. They are points of just unbelievable compression. So what would we even find if we could, somehow look inside one of these things? Let's take a little tour of a black hole's structure. Okay, right at the center, you've got the singularity. This is a point where matter is infinitely dense, and our understanding of physics just completely breaks down. It stops working. Around that, you have the event horizon. This is the big one, the point of no return. It's not a physical wall or anything, but once you cross that line, every single path leads to the singularity. No exceptions. Now, the part we can actually see is the accretion disk. That's that glowing, swirling disk of gas and dust getting superheated to millions of degrees as it falls in. It can glow brighter than entire galaxies. And finally, blasting out from the poles, you've got these incredible relativistic jets. These are just massive beams of plasma shot out at nearly the speed of light, and they can stretch for millions of light years. Just incredible. And you know what? Black holes aren't one size fits all. Not at all. They come in this incredible range of sizes, populating the universe everywhere from the core of galaxies to the quiet spaces between the stars. First up, you've got your stellar mass black holes. These guys are born when a single massive star collapses in on itself. Then there's this weird, elusive middle child, the intermediate mass black holes. We're still trying to figure them out. And then you have the titans, the supermassive black holes. These are the monsters lurking at the heart of pretty much every galaxy, including our own Milky Way. And just to give you a sense of scale, the event horizon of the big one in galaxy M87 is wider than our entire solar system. Mind-boggling.
So this leads to a pretty obvious question, right? If black holes are, well, black, if they're totally invisible, how do we even know they're there? Well, to find them, astronomers have had to become sort of like cosmic detectives, using all these clever indirect methods.
So, for one, we can watch stars whipping around at insane speeds, orbiting what looks like absolutely nothing. That's a huge clue. We can also spot the intense, brilliant glow of that accretion disk, the final meal of superheated matter before it falls in. Another amazing way is to watch how a black hole's gravity acts like a giant lens in space, bending and magnifying the light from stuff that's way behind it. And maybe coolest of all, we can now listen to the universe. We can detect the gravitational waves, these ripples in space-time itself that are created when two black holes smash into each other. We can literally hear them collide. For all we've discovered, black holes still represent the absolute edge of our knowledge. This is the arena where our two best theories about the universe, relativity and quantum mechanics, just collide. In this quote right here, it just brilliantly illustrates the central puzzle. Because just when we thought we had the basics down, Stephen Hawking came along and basically turned everything on its head with a discovery that mixes quantum mechanics with the physics of black holes. So here's the wild idea. Hawking predicted that right at the very edge of the event horizon, the vacuum of space isn't empty, it's fizzing with these pairs of virtual particles that pop into existence for a split second before destroying each other. But what if a pair pops up right on the edge and one falls in while the other escapes? Well, the one that gets away carries a tiny, tiny bit of the black hole's energy with it. This slow, steady leak is what we call Hawking radiation. And it means that over insane amounts of time, we're talking trillions and trillions of years, black holes aren't permanent. They will actually slowly evaporate. And this, right here, leads to one of the biggest, most mind-bending paradoxes in all of modern physics. Okay, so a core rule of quantum mechanics is that information can never truly be destroyed. It can be scrambled, but not erased. But if a black hole swallows information and then slowly evaporates into just random, featureless heat, what happens to all that information? Where does it go? Is it lost forever? Because if it is, that breaks a fundamental law of the universe. So this is where we're left, right on the very edge of cosmic discovery. What is the true nature of the singularity? Is information really lost forever, or does it somehow escape? And how in the world did these supermassive black holes grow so gigantic so quickly in the early universe? These are the kinds of questions that will drive the next generation of physics, pushing us to find a completely new understanding of space, time, and gravity itself. The journey is far from over.